Now we will continue our discussion of the one-dimensional finite element analysis, or I should say finite element analysis in a one-dimensional region. So here we have the very end of the previous lecture. We see that here are the here's the equation that we derived, and as was said last time, this is one equation in n unknowns, and when we vary I from 1 to n, we will get a total of n equations and n unknowns. So now what we'll do is look at the evaluation of the matrix elements. And recall that this here you see the definition of the matrix elements. So let's work with that a bit. Okay, so copying this equation, we have let's see, maybe I'll get away from a red marker here and let's see what we can do. Maybe we can go to a blue marker, let's see. Okay, so here I've merely transferred from above our expression for Mij, and now we want to talk about how this will be evaluated. Now, let's recall the following. Our problem domain looks like this. X is equal to 0 at the left boundary, and x is equal to L at the right boundary. And we have nodes which need not be evenly spaced, spread throughout this region. And we have agreed to call this first node node 0, and the last node is node n plus 1. So this is node n minus 1. Here is node 1 and 2, and so on. I'll put ... here in the middle. And recall that the well, let's do the following. Let's call this x1, and this will be x2, and so on. Here will be xn minus 1 and xn. So using that notation, then we would say that x0 is equal to 0, and xn plus 1 is equal to L. And all of the other x's would need to be stored somewhere if this mesh had non-uniform spacing. Now, if the mesh has uniform spacing and the spacing between any two consecutive nodes is delta, then we could just say, so I'll just say, in the case of uniform spacing, of delta, we could say that xj is simply equal to j times delta, because you see x1 here would be delta. See, since the first x0 is 0, x1 would be delta, x2 would be 2 delta, x3 would be 3 delta, and so on. But that's that equation is only good in the case of uniform spacing, and one of the real advantages of the finite element method is how easily it handles the case of non-uniform spacing. So in this discussion, I will not assume that that there is uniform spacing. I will assume that there is non-uniform spacing, and so somewhere your program has access to these stored values of x1, x2, all the way up to xn. Now, having said that, let's remind ourselves of one other thing. The basis function, let me actually change this picture just a little bit. Well, I didn't mean to do that, but that's okay. Let's say that this happens to be some node j, and here is node j plus 1. So actually, well, okay, so this is node j, this is j plus 1, and here is j minus 1. So this would be x j minus 1, and this would be x j, and this would be x j plus 1. And what we recall is that the basis function bj has the following form. It has a value of 1 at node j, and it goes down linearly to 0 at nodes j minus 1 and j plus 1, and everywhere else it is 0. So that's what bj looks like. And since we're bj of x, and since we and here I'll just put 1 to designate that the height of the function is 1, and since we are using the Larkin testing, this is also what tj of x looks like. And that information will allow us to evaluate these matrix elements. And again, now in evaluating these matrix elements, I, which is the index on the testing functions, we don't need to test at the two endpoints. So I is going to vary from 1 to n, but j can vary from 0 to n plus 1. Okay. So let's see what happens then when we evaluate these matrix elements. And I suppose the best way to do this is just to look at each term individually. So the first term here is just minus the integral 0 to L of dti dx dbj dx dx. And by the way, I think that once I do this, it may not be necessary to show all the details for the other terms, but let me at least show this one in some detail. So we want to integrate from 0 to L dti dx dbj dx dx. Now, the first thing we notice is that this expression could be written in a different way. Since we have dbj dx, let's think about that for a moment. Now, we have just said in this picture that is just above here, we've said that bj of x is non-zero everywhere except from xj minus 1 to xj plus 1. So if bj is 0 everywhere except in this little domain right here between xj minus 1 and xj plus 1, if bj is 0 everywhere else, then dbj dx is 0 everywhere else. So that means that really this integral only needs to go from xj minus 1 to xj plus 1. dti dx dbj dx dx. And one final time, let me explain. The reason for this is that dbj dx is 0 everywhere else except between xj minus 1 and xj plus 1. Now, likewise, dti dx, remember, since we're using Galerkin testing, this could actually be written like this: minus integral xj minus 1 to xj plus 1 of dbi dx dbj dx dx, because ti is equal to bi because we're using Galerkin testing. And now we also see something else important, which is that unless the region, well, let me back up and say, bi, just like the function bj is 0 everywhere except between xj minus 1 and xj plus 1, similarly bi is 0 everywhere except between xi minus 1 and xi plus 1. So unless those two regions overlap with each other, this first term is going to be 0. And in which cases will the regions overlap? Well, if we assume that, as we have drawn in this picture, that we number the nodes sequentially from 1 to n, going from left to right, then we can say the following: this first term will be equal to 0 if the difference, if the absolute value, actually, I'll put it like this just to make this perfectly clear. If I is less than j minus 2, or if I is greater than j plus 2. Now, another way you could write that is to say if I minus j, if the absolute value of I minus j is, actually, I can say 1, since I have strictly less than and greater than signs. So if the absolute value of the difference between I and j is greater than 1, that would be another way to write that restriction. But we're just saying here that if I is more than just one step away from j, see, if I is equal, like for instance in this picture, if I is equal to j minus 1, we would be okay, because b I minus 1 would be like this, and we would have overlap between the testing function and the basis function. But if say it were j minus 2 or j plus 2, if I were equal to either of those, then there would be no overlap at all, and so the term would be 0. So now, let's ask ourselves, well, what do we have if I is equal to j minus 1? And what do we have if I equals j? And finally, what do we have if I equals j plus 1? And that will cover all of the possibilities. So if I is equal to j minus 1, then the region of overlap will just be from xj minus 1 to xj. It won't be, now notice here, right up here, we have the upper limit of xj plus 1, but if I is equal to j minus 1, then bi, this bi right here, it won't stretch all the way to xj plus 1. It'll stop. So this is this case right here. Wait, let me try that again. It's like here. Here's an example of bi is equal to bj minus 1. So if I is equal to j minus 1, then we have a picture like this, and we see that the overlap just goes from xj minus 1 to xj, because bi does not extend beyond, or bj minus 1 does not extend beyond xj. So we don't have to integrate all the way up to xj plus 1, we just integrate up to xj. And so we would have b d j minus 1 for I, so dbj minus 1 dx, dbj dx dx. On the other hand, if I is equal to j, if it's the same, so we get rid of this now. And if I is equal to j, so that we have both functions look exactly like that, then we do indeed in that case have to integrate over the entire region. So we would have minus the integral from x j minus 1 to x j plus 1 of dbj dx squared dx. And finally, if I is equal to j plus 1, then in that case we would have something like this for our testing function. And so then the region of overlap would just be from xj to xj plus 1. So we have minus the integral from xj to xj plus 1 of dj plus 1 dx dbj dx dx. So these are the 5 different cases, or actually I guess you could consider it sort of like, well, yeah, I say 5 now because we have I less than j minus 1, I greater than j plus 1. Those are 2 cases. And then these 3 cases, I equals j minus 1, I equals j, and I equals j plus 1. So this is the first term in all of those cases. And so now let's see about the evaluation of these, which is actually quite easy. In fact, the first term is by far the easiest term to evaluate. So again, we get 0. That's already evaluated. If and we'll write the restriction like that. Now, what about this next one? When I is equal to j minus 1. Well, we have negative, here we have, we're looking up above now, and we have negative the integral from xj minus 1 to xj of dbj minus 1 dx dbj dx. So let's just, we'll just draw a little picture over here to help us remember exactly what this looks like. So here is node j minus 1, and here is node j. Now, in the region between, well, actually, I'll keep with the same constraint I had before, or same agreement. Oh, this is node j, and this is node j minus 1. I'll put the node numbers above and the coordinates below. So this is x, this is x, j minus 1, this should be j, and here's x, j minus 1, and here's x, j. And remember now, bj looks like this in this region. It goes up to 1. But bj minus 1 will look like this. Again, this is bj, and this is bj minus 1. So, we have integral from x j minus 1 to xj. Now, dbj minus 1 dx is the slope of bj minus 1 in that region. Now, so we're just looking for the slope, again, looking right here. We're just looking for the slope of that line. And so the slope of that line is 0, which is the value at the end, minus 1, which is the value at the beginning, over xj minus xj minus 1. Just that simple. And on the other hand, dbj dx is 1 minus 0 over xj minus xj minus 1. Again, we have dx. So you can see right away just how simple that is. Now, the same kind of thing will happen on the next integral, but I'm going to break it up into two parts. So I'm going to write the next integral as minus the integral xj minus 1 to xj of dbj dx squared dx minus the integral from xj to xj plus 1 of dbj dx squared dx. And of course, the reason I'm breaking it up like that is that dbj dx has a different expression over the first part of the region from what it has over the second part of the region. So that will make it easier for us to evaluate that. But the last integral is ready for us to go ahead and evaluate. So we have minus the integral, and again, just as before, we'll draw a little picture here. So here is node j, here is node j plus 1, and so we have bj looks like that, and bj plus 1 looks like that. So we have integral xj minus 1, excuse me, xj to 2xj plus 1. Okay. And we have dbj plus 1, so that's the slope of dbj plus 1 is 1 minus 0 over xj plus 1 minus xj. And the slope of bj is 0 minus 1 over, and this is of course xj plus 1, and here's xj, so xj plus 1 minus xj dx. And we're getting close to having this all done for the first term. So, first term equals, okay, so we have 0 if I minus j greater than 1. Okay, now the next one, we have a negative sign, and we in the interior, all that in the interior of the integral is a constant, so it can come out, and it's equal to negative 1 over xj minus 1 squared. So that negative 1 will go with this negative sign out front to give us a positive 1. So we just have 1 over xj minus 1 squared times the integral xj minus 1 to xj of 1 dx. And that is if I equals j minus 1. And by the way, this one is if I equals j plus 1. Okay, now let's go to the case if I equals j. What does that one become? Well, we get minus the dbj dx between xj minus 1 and xj. Okay, it's going to be a constant, so we can pull it out. And so it will be 1 minus 0 over xj minus xj minus 1. And that's all going to be squared. And then we'll have integral from xj minus 1 to xj of 1 dx. And then we also have minus, and following along the same way, we'll have 0 minus 1 over xj plus 1 minus xj squared integral xj to xj plus 1 of 1 dx. And then finally for this last one, we will have 1 over xj plus 1 minus xj squared integral xj to xj plus 1 of 1 dx. That's if I equals j plus 1. And so now we finally wrap this all up and see just how simple this is. So we get 0 if the difference between I and j is greater than 1. We will get 1 over xj minus xj minus 1 if I equals j minus 1. We will get minus 1 over xj minus xj minus 1 minus 1 over xj plus 1 minus xj if I equals j. And finally, you will get 1 over xj plus 1 minus xj if I equals j plus 1. And that concludes our discussion of how to evaluate the first term. And everything for the second term and the third term up here would be very similar, except that now, for the derivatives, you know how to do that, but for the function, you would have to find an expression. It is the ti's and the bj's are piecewise linear functions, but since you know the value of each function at each endpoint of each interval, and you know the endpoints of the intervals, you can pretty easily find those expressions. For instance, just to give one last little note on that, let's just say it this way. Let's say that this is node j and node j plus 1, and here's node j minus 1, and so here's xj minus 1, xj, and xj plus 1. Well then, now remember that bj will look like this. So suppose that we want to find a functional expression for bj of x. Okay. Well, bj of x is equal to 0 if x is less than xj or j minus 1, or x is greater than xj plus 1. And then we have to consider two more cases. If xj minus 1 is less than x is less than xj, and then the final case will be, actually let me move that over to the right, give me more space. So we'll say if xj minus 1 less than x less than xj, or if xj less than x less than xj plus 1. So we just have to find expressions for bj in each of those two formulas, each of those two regions, and let's see. I believe that we can say x minus xj minus 1 over xj minus xj minus 1 is a good, is a valid expression in the region between xj minus 1 and xj, and in the region between xj and xj plus 1, I believe we should say xj plus 1 minus x over xj plus 1 minus xj. And so that's how you would find expressions for the functions, and you could use those up here in evaluating the second term, which in that term here, I'm calling this the second term, the one with P, or this one with Q is the third term. But for right now, we have evaluated the first term completely, and it's right there. And so if any more help is needed in evaluating the second or third term, we can discuss those later. But that's it for right now. And so good luck.